So this is a little presentation on the history of number systems, and try to give you an idea about the continuing, ongoing introduction of new number systems from time to time. And so the learning objectives are to summarize what we've already learned about the gradual introduction of new kinds of numbers, which have repeatedly extended the older ideas of number to include broader concepts, and to become aware that this continues with number-like objects such as quaternions, tensors, spinors, matrices, serial numbers, p-adic numbers. New things get created as applications call for it. Or sometimes things just pop out from the logic. You realize, oh, this has to exist. So, started with counting sheep. Natural numbers were used for that. And so we've learned about the Egyptian, Roman, Chinese, Babylonian, Mayan, Hindu, Arabic, and binary digital systems for representing those numbers, the kind that you count sheep with. And then 0 was introduced as an accounting symbol to indicate neither ownership nor debt. So it was used in Egypt in 1770 BC. It was separately introduced in other places, but as just a placeholder. So in these place value systems, now you may remember the Egyptian system was not place value. Their 0 was just 0. But in the place value systems, sometimes they needed a placeholder. You know, like if you were in the Babylonian system and you'd say, okay, I have 25 ones, and I don't have any groups of 60, and then I have two groups of 3,600, right? So they needed a placeholder for I don't have any groups of 60. So they had a symbol. It wasn't part of what we covered because it was a little bit later. But they had a symbol for 0, but they didn't think 0 was a number. It was a placeholder that they stuck in the middle of writing a bigger number just to show that there was a space. And so that also popped up in the Mayan number system and in the Incas and in the Chinese numerals. And in all of those cases, these were place value number systems that needed to write something when a place was empty, but they were not thinking of 0 or using it like a number, and it would never appear just by itself. And then as a real part of the number system, it was used in India around 500 to 700 AD, and it found its way from there through Persia and into the European culture. So that's the 0 that came, into the curriculum. So after the 0, we have negative numbers, the integers. They're still just whole numbers, but the negative ones as well. So I don't want to say whole numbers. I should say the right word. It's integers. And so there was a usage about 200 BC in Han Dynasty, China. I think I read this was under an Empress Wu, who introduced negative numbers to indicate debt. And there was a system of counting rods. You had beads on a rod. You may have seen an abacus. And so what they would do is they had the red rods and black rods. So the red rods were for positive numbers. I'm not sure which one was which, I forgot. Anyway, I'm wondering if this is the origin of the red ink idea, but you'd have two different rods, one for your negative numbers and one for your positive numbers. And then used to represent debts in India around 700 AD. And I was surprised to find out that resistance to negative numbers continued up until the 17th century. There was this idea that it's not really a number, it's a positive, okay, it's an amount of debt, so we'll put a little symbol in front to make it debt, but apparently people didn't want to think of it as just plain numbers. And I think what makes it make sense to think of a negative number as being a number is that you can do all the arithmetic with it. You've got the rules for, okay, here's how I add and subtract one of these things. Here's how I multiply and divide. And you can, when you throw in the negative numbers, all those commutative and associative and distributive properties you may have learned about in algebra in your youth, all that stuff still works. And so eventually people decided, yeah, you just consider them part of the number system, and why is -5 any less a number than 5 would be? So you get around to sharing stuff, fractions. You share 3 pizzas among 4 people. How much does each person get? Well, you write this 3/4, you make a fraction. You're familiar with that, okay? But if you could try to put yourself in the frame of mind of either a child who's first seeing it or historically when it first appeared, it was a big deal because people would naturally want to say it's not a number. It's 2 different numbers with a slash in between. That's not a number, they would say. You want to say, well, but it's how much pizza each person gets. It's an amount. Well, okay, maybe. But what makes it a number is, once again, you can come up with the rules for how to add and subtract them. So yeah, it's 2 of your old numbers with a slash in between, but it gets a whole new set of rules for doing the arithmetic. And those rules continue to obey the commutative, associative, distributive properties. And it includes all the whole numbers. They're fractions too, because a number like 5 is like, 5/1. So you've got a thing that still obeys all the same rules, includes what you had before, and you can do all the arithmetic with it. So you may as well call those numbers as well. And so by the time you get to, Pythagoras, he was very comfortable that these fractions are numbers, but he was not comfortable with negative numbers, and he was not sure that 0 should be considered a number either. Okay. So the Babylonians had a system for using these, and the Jain people in India had a base 10 decimal number system, and they had fractions, and they were making approximations for pi and the square root of 2 and this sort of thing. Now, I think they were not sure if maybe, like, you're looking for the square root of 2, you say, okay, 1 is too small, 2 is too big 2.5 is too big. I'm sorry, 1.5 is too big. Okay, well, 1.25, go back and forth, halvesies, cutting it in half, narrowing it down. I don't think they were sure whether you would ever come to an answer. Maybe if you could just keep going long enough, you might eventually come to find, the exact decimal. And so even up through Pythagoras, the assumption was that, there's a lot of digits, but it's just a fraction, and therefore it will terminate or repeat at some point. Okay. So Pythagoras, 550 BC. Now that we've shared stuff and we've got fractions and we've got negative numbers for debt, although we still argue about whether they're really numbers, he says, well, you want every possible distance to be a number. And that let him do things like the Pythagorean theorem, on a triangle, on a right triangle, you square the height, you square the width, add them together, and that gets you the square of the hypotenuse. So by thinking of distances as numbers, he could facilitate surveying and all sorts of other things. But Pythagoras thought when he said numbers, he meant fractions. And so he figured there would have to be a fraction for every possible distance. And one of his students, Hippasus, proved that there's no such fraction. Now, his proof was lost, but it upset the Pythagorean school, because Pythagoras had been very clear that numbers are fractions and there is one for every possible distance. And then Hippasus comes along and says, no, there's not any fraction that'll do your square root of 2. The length, the distance across the diagonal of a square. There's no fraction for that. And somehow it upset people. Anyhow, he was possibly killed. There's some stories that were written down like 800 years later saying he got thrown off a boat and drowned. It wouldn't stand up in a court of law. We probably don't really know what happened. But then Euclid, another 100 years later, 350 BC, he wrote a really nice proof that the square root of 2 is not a fraction. And it was unclear at the time, well, what else could it be? But unlike the Pythagoreans, he was willing to say, well, look, if it's not a fraction, it's some other kind of number. Maybe we just need more numbers. And that's really the right attitude, because it's I don't want to say it's routine, but it's happened repeatedly that the thing to do for new applications is just extend your number system. And when I first learned this, it was really surprising. It was not until 1860 when a mathematician named Weierstrass finally answered that question. Well, if it's not a fraction, what else could it be? And he made a real modern, rigorous construction of the real numbers. And I'm not going to do that one, because you'd have to learn calculus first. And that's why it took so long, because, mankind had to learn calculus first. And then you could then they could figure out what's a real number really. So that's my summary of the history. It continues. We've got complex numbers. So they were introduced in 1545 as a convenience in doing algebra. So this Cardano guy was factoring polynomials, third-degree polynomials, and he needed a placeholder. And so he stuck in this I thing, like a square root of -1. The number that when you multiply it times itself, you get -1. And he called it imaginary. You know, he says, this is not actually a number. It's just I can use it in the algebra, and it's really convenient. And de Moivre found that, hey, well, it's not just convenient in algebra, it's convenient for geometry and trigonometry formulas. And then turns out it's got a connection to geometry, and you can make it really concrete, really understandable what this thing is. So just like the negative numbers and the fractions and the real numbers and so forth before it, you know, it just gets thrown in to make the number system bigger. And it's been very useful in electrical engineering and physics, and with all kinds of phenomena that involve cycles, going around in circles. So that's your complex numbers. And then in the 1970s, we got the surreal numbers. And well, I'm jumping all over time. There were quaternions, but that's way back to Hamilton in the 1860s. Tensors, anyway, it's a menagerie of different types of numbers. But you can do arithmetic with all of them, and all the same rules work, and they just keep extending the ones you've already got to include what you already had and a few more things besides. Okay. So that's it for the slideshow. And I'm gonna stop the recording.